Good afternoon, everybody. We're just going to wait a few moments for everyone to join, and then we'll make a start with this webinar. Okay, it looks like everyone who's joining has joined. So thank you again, everyone, for joining this webinar, and welcome to the webinars for the Davidson's Inventors Challenge. This is our final sort of part of the competition, where we have 4 teams which have been shortlisted who are going to be doing their presentations, and we're going to be selecting a winner from these teams to be awarded the competition as the prize winners for the competition today. So the whole idea of this this sort of competition, really just to give you an idea of why we run this competition, is to really give an opportunity for students which are in their early parts, well, they're either in their year 11 or year 12 of their education, an opportunity to really experience what chemical engineering and biotechnology is all about, and what does the discipline involve, and the diversity of the discipline. So the competition is really focused around the Sustainable Development Goals and why chemical engineering and biotechnology has such an important role in addressing some of these Sustainable Development Goals. So just before we kick off with the presentations, I thought it'd be important just to kind of make a few announcements and say thank you to some of the people who've been contributing towards this competition and initiative. First of all, I really would like to thank our partners, the ICME and ASTI, who is based in Malaysia, and particularly Dr. Yunus Yassin, who runs ASTI there, and all their support and involvement in the program. Without their help and their time, we wouldn't be able to put this program together. The other thing, we really want to thank all the students and all the schools which have really got involved in this program. We've had over 45, 50 schools participating in this program, over 300-400 students which were involved in this competition. It's great to see such a large range of students sort of engaging in this competition and learning about chemical engineering and biotechnology as a subject area. The other thing, we've had a lot of mentors involved in the program who've been helping out with the running of the program, assessing all the entries coming in, and basically providing feedback to all the students about their entries. So I just really wanted to thank all the ICME members and all the undergraduates and graduate students who have been involved in running and providing these sorts of feedbacks and assessments for us. Lastly, I just want to make a special thank you to our guests, the ICME president, Mark Epsey, and also Gavin Patterson, who's an alumni from the department, who's joined us today. And also, I just wanted to say a big sort of thank you to the Davidson family, and we have Peter Davidson here as well with us today, for their continuous contribution and support to this program. And the key thing I wanted to announce is, due to the generosity of the Davidson families, we are now being able to award a £300 prize for the winning team today as well. So just to kind of go through the agenda. So I'm going to be just wrapping up here with sort of a welcome. I will be chairing the session, so feeding all the questions that will be coming in between the presentations as well. After my short introduction here, I'm going to be passing over to Professor Jeff Mogridge, who's going to give you a short introduction into the department and the relevance of chemical engineering and biotechnology in Sustainable Development Goals. And then I'm going to pass over to Sir Peter Davidson to talk a little bit about Professor John Davidson and the important role he's played over the years in the Chemical Engineering and Biotechnology Department at Cambridge. And then around 3:30, we're going to kick off, and we're going to have our 4 finalists give their presentations in the order shown in this slide. And around 4:30, where hopefully we'll be able to get through everyone's presentations, we're going to take a short 15-minute break. Please don't dial out the call, just keep your cameras and mics off. And once the judges have finished deliberating, we're going to come back and do, Gavin Patterson is going to give us a short talk about his experience in working in industry, and how hopefully talk a little about why chemical engineering has been a great advantage for him and how that's helped him in his career. And then hopefully move on to wrap up and have an announcement from the president of the ICME about the winning team. And so we'll be able to do the announcements and awards of the certificates at the end and close the ceremony at that point. So that's the schedule for today. Just before I pass over to Jeff Mogridge, just wanted to make some important notices. This event is being recorded, so please be aware of that. Everyone's mics and videos should be muted and off. Unless you are going to be a presenter, you won't be able to turn on your mic or video, so please be aware of that. There is a Q&A box feature on Teams. Please make use of this during the presentations. If you wanted to post any questions, I should be able to pick those up, and each team will be presenting for 10 minutes, and there'll be an opportunity for 5 minutes to ask any questions to the teams. And just the last thing about safeguarding notice, if there are any concerns and you would like to be able to raise those, the moderator designated safeguarding lead is Alana Gonzalez, and her email address is given here on these slides. So I'm going to stop sharing my slides now, and I'm going to pass over to Jeff Mogridge.
Hello, so welcome to the Davidson Inventors Challenge on behalf of the Department of Chemical Engineering and Biotechnology in Cambridge. So I just first want to really reiterate Cam's thanks to all the people who've made this event possible, in particular the mentors and the supporters, and obviously the partners. Again, that's the IChemE and the Association of Science, Technology and Innovation of Malaysia, and of course the very generous support of the Davidson family. This challenge has been now running, this is its 4th year. It's been very successful, and it's continuing to be very successful, and of course we're very pleased about that. But I'm also very pleased that it's in memory of John Davidson, who's someone I knew well. He was past head of department, and of course he's one of our most distinguished alumni. We're very honoured to have Peter Davidson, his son, here. He's going to tell you more about John's life and work, and so I won't do any more along those lines, except I would like to say how much I think John would have enjoyed this event in particular as something in his memory. Obviously the focus of the event has been on achieving sustainable goals. And that fits really well in with the department's ethos. So there's an enormous amount of research that goes on within the department in a very wide range of fields, but our 2 particular research themes of focus are sustainable energy and healthcare. And of course, both of those are absolutely central to sustainable goals. I think we've got 4 teams of finalists here from Northampton School for Boys, Twycross House School, Atherstone, King Edward VI Camp Hill School for Girls, Birmingham, and Bishop Stortford College. So a really warm welcome to you in particular. This has been a really competitive competition. So you've all done extremely well to get to this final. And so certainly as far as I'm concerned, whatever happens today, obviously only one team can win, but as far as I'm concerned, you're all winners by virtue of having got this far. So congratulations already, and I hope it goes well today. So I don't want to spend much longer, but I just want to give you one example from history of why innovation in chemical engineering and biotechnology can be so important, and in particular can be so important in achieving results in sustainable development goals, in this case, healthcare. So I'm sure you've all recently seen in the news that we've just had the 80th anniversary of the D-Day landings, which happened on the 6th of June 1944. So I hear you cry, what has this got to do with chemical engineering? Well, it was the first time that there was a large-scale use of penicillin in history, apart from many other things about the D-Day landings. So penicillin was discovered, as I'm sure many of you know, in 1928 by Alexander Fleming. It was then tested on animals and then on humans by Howard Florey and Ernest Chain, not until 1939. But at that stage, nobody knew how to make it in sufficient quantities that you could actually use it in anything other than a lab setting. And there was a really desperate effort prior to the D-Day landings to make sure that they had enough penicillin available to treat all the casualties they were expecting at the D-Day landings. And there were two groups of people in particular who were important in achieving that. One was Margaret Hutchison Rousseau. So she ran the plant that did the first commercial production of penicillin. And actually, the plant was itself built in 1944, so really just before the D-Day landings. And she invented deep broth fermentation reactors. So these are 10,000 litre fermentation reactors in which the penicillin was grown. Prior to that, all they'd been able to do was grow penicillin on agar plates, which many of you may have used in the lab. So this allowed quantities to be produced sufficient to treat large numbers of people. She, of course, was also a very interesting woman for other reasons. She was the first woman in the US to get a doctorate in chemical engineering, which happened in 1937. And she was the first woman to become a member of the American Institute of Chemical Engineers. That's the American equivalent of the IChemE, who are represented here today. And that happened in 1945 as a direct result of her work on penicillin production. So that was the production of the penicillin. Once you produced it in these reactors, it's at a concentration of around 50 parts per million. That's something around the concentration of bromine in seawater. And moreover, there's 1,000 times more other stuff in there than there is the penicillin, which you want to take out. So the separation process, which also had to be designed from scratch, is as difficult as making the penicillin itself. And that was designed by the Shell Development Labs in California, again, a group of chemical engineers. So the net result of this was that they produced 2.3 million doses of penicillin in time for the Normandy landings, and it's reckoned to have saved 12 to 15% of the casualties on those landings on the Allied side. So this was an effort sort of equivalent to what we saw more recently with the COVID vaccines. So anyway, that's just one example of what can be achieved by innovative thinking around chemical engineering and biotechnology. So I don't want to take up any more of your time. I'll hand over now to Peter Davidson. Thanks very much for telling us something about your father.
Thank you. Elena normally had a photo of my old man to put up. If you can imagine a young Geordie lad coming up to Cambridge in 1939, the only reason he got into Cambridge at that time was because in the Second World War, the university was still bringing in engineers and physicists, and had forgone the criteria that they should do Latin because his school didn't do Latin at that time. He got every single academic prize it was possible to get and came top in 2 years rather than 3 years in the engineering tripos. So unlike Gavin or myself, who didn't do quite so well, he could actually say afterwards, well, it doesn't matter so much what your first degree is, it's what you do with it. Most of his life, he started off in the young chemical engineering department, which was mainly recruited by engineers and chemists. There was a formidable head of department who was more interested in the quality of the people than their background, and said the best way of learning chemical engineering is to teach it. But he produced very concise analytical models, choosing the right simplifying assumptions, and he'd be delighted with the 4 projects that are up today, through an understanding of the transport processes and mechanics. And he helped to establish chemical engineering as a proper discipline at Cambridge in its formative years. In the early days in Cambridge, people said, well, Cambridge should just be interested in pure science. Applied science doesn't have a place. And over the years, he worked on bubbles a lot, and is said to be the father of fluidization, which is used for the manufacture of all sorts of things. And indeed, some of the reactors he worked on, which I worked on later at Billingham, are now used for the production, were used for the production of some of the COVID vaccines as such. He was the youngest president of the IChemE in the last 90 years, vice president of Royal Society, and a foreign associate of the Indian National Academy, the Soviet Academy of Sciences, and so forth. So he was quite a big wig in that context, but he never lost his sort of mild manner. And students coming for supervisions or for tea in my mother's garden would be surprised sometimes to find their bikes had been repaired by him when he thought they were unsafe. And on the safety front, he was one of the panel members of the Flixborough Court of Inquiry. He wouldn't have approved of the post office inquiry. He would say it would take far too long. But that set the standard of detailed technical investigation of the different causes of the Flixborough explosion, which killed 29 people, and was pretty well the biggest peacetime explosion ever to take place in the UK. And that approach improved safety in numerous plants all around the world. He maintained lifelong friendships with foreign students, and he was pretty dismissive of what he termed academic engineers, be they chemical or anybody else. He applied his chosen field in practice as a real engineer, rather than, in his words, an engineering scientist. And he used to delight in constructive discussion between the academic and industrial communities in the society. And he was one of the driving forces behind bringing chemical engineering and biotechnology together at Cambridge, which has seen the fruit in the development of a number of new biochemical processes. So he and I were the only father and son fellows of the Royal Academy of Engineering. I'm not an FRS, which he certainly was, aside from one other pairing in the history of the Academy. And if you can think of chemical engineering as being something which is interested in the fundamentals, but interested in the real world and solving real world problems, you'll be on the right track. He and I together did a few things about the Institution of Chemical Engineers research event. And a memory that I treasure is that after we'd given a bit of a boost to that, we invited Jonathan Porritt along to the assembled gathering of about a third of the UK PhD students in chemical engineering. And Jonathan stood up and said, well, it's all very well for me to talk about the environment, but you real engineers are going to be able to do something about it. I think that's as true then, true now as it was then. So well done in advance for all your contributions, and I hope you can enjoy the rest of the process. Thank you.
Thank you very much, Peter, and thank you, Jeff, for the kind introductions. Okay, so I think we now can proceed with our first team speaking. So I would like to invite Team Agisa, I hope I've got that all right, to come online and share their screen and start their presentations. Team Agisa, are you here? Ah, there we are. Brilliant, we can see your presentation.
Okay, can you hear us?
We can hear you okay.
Okay, brilliant. So, good afternoon, everybody. We are Team Agesa from Northampton School for Boys, and we would like to thank you for having us. We hope to present our case for the use of bacterial cellulose as an alternative absorbent in sanitary products. Menstruation is a biological process which currently affects 26% of the global population. Thus, it is important for menstruating individuals to manage menstrual flow and use a hygienic form of menstrual protection. Typically, menstruating individuals from lower socio-economic backgrounds have a lack of access to sanitary products, and this reinforces the negative perception around menstruation. This leads to many barriers towards education attainment and gender equity, therefore reducing the access of sanitary products. Petroleum-based superabsorbent polymer, commonly referred to as SAP, is used in an absorbent layer of commercial sanitary pads. However, the machine, capital and energy required for the production process contributes to the cost of pads and makes it unaffordable to those from lower socioeconomic backgrounds. Petroleum-based SAP causes irreversible damage towards the environment. Sanitary products, which are typically disposed of in sanitary bins or general household waste, cause landfill buildup and may take 500 to 800 years to decompose. The transition to biodegradable alternatives is a promising solution which would alleviate strain on landfills and mitigate environmental impact associated with non-biodegradable SAPs. As a result, our solution would reduce the number of people using traditional and unreliable absorbent materials, including old clothes, paper, and leaves, which could lead to urogenital infections and other severe health conditions, such as toxic shock syndrome. Increased access to biodegradable sanitary napkins promotes good health and well-being through menstrual hygiene, so that health equity does not come at the expense of environmental sustainability. As our proposed solution is single-use, it avoids the need to be washed with clean water that is required for reusable alternatives. Improved access to menstrual protection would help to reduce social and cultural stigmas around menstruation via biodegradable alternatives, and hopefully provide menstruators with equal opportunities to reach full potential at both school and work.
Our solution to the problem of poor access to affordable and sustainable sanitary hygiene in developing countries is to develop a sanitary pad with bacterial cellulose as its absorbent layer. Bacterial cellulose has several advantages over alternative materials for sanitary pads. In addition to being biodegradable, it can be produced at a low cost using bacteria, which are a renewable resource. In contrast, the crude oil needed to synthesize SAP is non-renewable. The production of bacterial cellulose is also more sustainable than the production of plant-based biopolymers, such as cotton and bamboo, because these require large amounts of land, water, and fertilizer. This is expensive, and it has adverse environmental and societal effects, such as habitat destruction, eutrophication, and the loss of land for food production. Finally, the purity of bacterial cellulose means that it requires significantly less chemical treatment than plant cellulose and other plant-based biopolymers. This treatment is both expensive and environmentally damaging. As such, we feel that bacterial cellulose is a promising alternative material to those currently on the market. At an industrial level, bacterial cellulose can be produced continuously by agitated fermentation using what is known as Hester-and-Schramm culture medium. This has a slightly acidic pH of between 3 and 7 and is rich in both glucose, which is used for respiration, and peptone, which is used for DNA replication and protein synthesis. So as you can see on the left, the discs are partially submerged in the culture medium. As the bacterial cellulose is produced, it attaches itself to the discs, which are spun in order to agitate medium. This increases the efficiency of the process and thus the yield by ensuring the medium remains homogenized. To lower the cost, static fermentation may be used instead. This process produces bacterial cellulose in batches as opposed to continuously, and is consequently slower. However, due to the more basic apparatus needed, the cost is lower. Cost can be reduced even further by using a culture medium made from organic waste. On the left, you can see our attempt to make bacterial cellulose from kombucha-derived culture medium. The bacterial culture itself can be bought online for a low price. The culture medium only required tea bags and sugar, and the apparatus used was extremely basic, consisting of only a plastic tub. As such, this process can very easily be replicated in low-income countries, ensuring that the technology remains accessible to all. Our research further highlighted that the use of a culture medium derived from mango peel extract in particular could increase the yield from bacterial cellulose by up to 2.5 times, further increasing the cost-effectiveness of our proposed solution. So according to our research, each sanitary pad would require roughly 1.1 grams of bacterial cellulose. If using Hester-and-Schramm culture medium, 2.14 grams of cellulose are produced for every litre of medium used, meaning 514 millilitres of culture medium is required to produce enough bacterial cellulose for one pad. So on the right, you can see a list of the components required for the Hester-and-Schramm culture medium. The mass of each component required for both 1 litre of culture medium and 514 millilitres and the cost per gram of each material, as well as the cost needed to manufacture one pad. So according to our calculations, this places the cost of pads at roughly 33 pence, making our proposed product competitive with those currently on the market. The small-scale production techniques mentioned on the previous slide can reduce the cost even further, both due to the lower cost of the medium and apparatus, and because, as mentioned previously, some alternative culture media can produce higher yields of bacterial cellulose for the same volume of culture medium.
Our product has been designed to contribute to the 5 Ps in many ways. Through our sanitary pad, we aim to reduce the stigma around menstruation through raising awareness around issues surrounding menstrual hygiene. This addresses both peace and partnerships. A lack of access to sanitary products causes women to miss out on education and keeps them from work. The provision of menstrual hygiene, therefore, ensures that they are better able to take part in the economy and guarantee their own financial security, aiding in prosperity. Furthermore, better access to sanitary products brings many other material benefits to women, such as the ability to participate in the economy, as already discussed, as well as a lower likelihood of infections, which addresses people. In addition, the production is more sustainable and creates biodegradable sanitary products, which reduces the adverse environmental consequences of landfill waste, as well as having a lower carbon footprint to produce than existing sanitary products, through which it aids in reducing our impact on the planet. In summary, there is currently limited access to hygienic forms of menstrual protection to manage menstrual flow in many low-income countries worldwide. In addition, current products often end up in landfill or are incinerated, impacting the planet. In our product, the properties of bacterial cellulose make it ideal for the absorbent layer, and as the manufacturing process becomes cheaper, it will become a safe, accessible, and sustainable alternative for current sanitary products, which will ensure that gains in health equity do not come at the expense of environmental sustainability. Thank you.
Fantastic. Thank you so much for your presentation. So I'd like to open this up now for any questions. So do any of the panelists have any questions they'd like to ask? You can post them on the Q&A for any of the participants as well, or in the chat, whichever would work for people. While we wait for some questions to be posted, I have a question for everybody. You've got your reactor set up. I could see you've kind of done a demo in the lab there, and you've got something sort of stirring around and culturing and growing. Have you thought about how that could be scaled up? How would that look on a large scale?
So when we're looking at this continuous process, the way that we would scale this up is by looking at expanding the reactor size and expanding the size of the spinning components of the reactors so that we have this agitated fermentation on a much larger scale and on multiple layers to produce a much greater area or greater quantity of bacterial cellulose on multiple layers that can be extracted through this continuous process.
And sort of what sort of time scale do you think it would take to, you know, in the big batch process to have this sort of cellulose growing on this sort of continuously rotating sort of structure?
So for that, we would have to consider perhaps the fermentation time and how long it actually takes for the bacteria within the culture medium to produce the bacterial cellulose that attaches to the spinning discs. And on our estimations and on our research in the paper, we found out that this takes roughly 10 to 15 days, and we can either speed this process up or slow this down by alternating different factors within the culture medium, or even just the environment as a whole.
Okay, I could see there's a question posted in the chat here. How have you evaluated the commercial aspects for scale up and globalization?
Sorry, could you just repeat that? Sorry, it just cut out for a bit.
So the question is, how have you evaluated the commercial aspects for scale up and globalization?
Okay, so with the adoption of bacterial cellulose as a product, since we're using bacterial cellulose as the absorbent layer, there may be some resistance with the product, but we would ensure that through the chemical processing that goes on in the process and the treatment that undergoes the bacterial cellulose. We ensure that our products is both safe and applicable for both a small scale on these local communities and a much larger commercial scale, since that scalability between the two different fermentation processes, the agitated fermentation and the low scale fermentation, there's that ability to scale up on a global scale.
Okay, brilliant. Peter, did you want to ask your question? Oh, you're on mute. You're still on mute. While we wait for Peter to figure out the mute, consumer behavior. How would you deal about consumer behavior in terms of your marketing, especially in the third world? Have you given that much thought?
Well, the idea with cultural and social stigma is that there's already a lack of access to sanitary products. So we discussed that there's many different options, such as old clothes or even like leaves and such. We believe that if we increase awareness of menstrual hygiene, it will get people more talking about menstrual hygiene. And then when people are more open about these sorts of issues, the cultural stigma tends to, I don't really know how to say it, well, kind of resolves itself in a way, because more people are able to talk about it and they're able to have access to sanitary products.
That's it. Peter, did you want to ask your question?
Yeah. So at the moment, the market for superabsorbent polymers is, I think, of the order of 10 billion a year. One of the things that's going to affect the cost base is how big a reactor you need and how much you can put through it. Now, those sorts of reactors are normally affected either by the diffusion of the raw materials into the bugs or yeasts that are producing material, or they're affected by mixing. Did you look at all at what determined the size of the reactor and what were the rate controlling steps?
So when we considered the two different fermentation processes, we realized that the small scale production that we discussed earlier, the largest issue that came up with it was that there was a significant limitation on the amount of bacterial cellulose that could have been produced. Since bacterial cellulose forms at the air-liquid interface between the culture medium and outside the reactor, the rate of bacterial cellulose production is limited by factors such as oxygen and just the size of the culture medium. So then we looked into the alternative fermentation process, such as agitated fermentation, where described earlier we had the spinning rotating discs, which can be scaled up on a much larger scale. And although, again, this would be limited by the culture medium and how much culture medium we can actually put into that reactor, the size of our reactor would be suitable enough to produce on a much larger industrial scale in comparison to the small scale production, which is limited by other factors such as not enough oxygen diffusion into the culture medium for it to be efficient to produce on a larger industrial scale.
He would have loved that answer because he spent quite a lot of his life on bubbles and creating sets, but I better not put your leg on that.
Okay, guys, so one last question before we move on to the next team. There's another one come up in the chat. What environmentally friendly products are already on the market, and how does your compare commercially?
Well, environmentally friendly products would be reusable sanitary products, such as like menstrual cups that you've seen, and like reusable pads that you can actually wash in the, well, just wash in general. However, menstrual cups tend to be quite expensive and it's not as accessible as sanitary products, for example, like normal pads and such. However, with reusable pads, there's the aspect of cleaning, and in lower socioeconomic countries, you lack the water and sanitation required to clean, as there's not enough clean water to clean through. So this could lead to bacterial infections within that could build up in this pad.
And to just further develop that point, if we look at other biodegradable materials such as bamboo and cotton that was mentioned in the presentation, the largest issue with those biodegradable products is that the amount of land, the amount of time, and other factors such as the fertilizers and the environmental impacts of the fertilizers. So you have these knock-on effects in the whole life cycle of the other biodegradable products, which are reduced when you look at bacteriocellulose.
Brilliant, fantastic. Thank you very much, Team Agisa. Thank you very much for your presentation. I think we'll now wrap up. We're now out of time, so we'll move on to the next team. So now I'd like to invite the next team, which is called the Lab Techs. The Lab Techs, please come online and start sharing your screen. I can see your screens come up. You might want to put it into presentation mode.
If you pop it in presentation. There we go. There we are. Sorry about that.
That's good. It's there, and we can hear you fine. So make a start whenever you're ready.
Hello, I'm Henry Thomas.
I'm Amy Downs.
I'm Elliot Lewis.
And I'm Gracie Tompkins. And our sustainable development goal that we have selected is affordable and clean energy. The UK, and well, really every one of us here, has a target of net zero by 2050. But most of the heating for housing in the UK is done using gas, which currently is methane. Between 70 and 80% of housing uses gas, resulting in about 31% of overall UK emissions. The cost of gas and electric varies significantly, with 6p per kilowatt of gas versus 26p per kilowatt in electric. So, electrifying heating will impact us all financially. Well, we're parents who moan about the bills, maybe every day, sorry dad, and may push people into fuel poverty and increase risk for the vulnerable. Are people willing to pay this cost? Energy is a hot topic and a huge challenge, be that the cost I mentioned, the environment, sanctions, geopolitical and war over resources. Our project, however, doesn't solve this, but it focuses on one of the many engineering problems associated with the transition to clean and affordable energy. The UK has pipes to over 21 million homes, transporting methane predominantly for heating houses. If these could be repurposed to transport hydrogen, then the road to net zero could be possible. The problem is that these pipes were designed and built for methane. They are also designed taking into account diversity, which is that not everyone will be using it at the same time. Imagine everyone flushing the toilet simultaneously. The water pressure would drop, or every kettle going on at the same time. Infrastructure is designed based on typical use. The electricity network is now struggling currently as they have saver sessions, where they reward customers to use less energy at peak times. That's my dad telling me to turn the lights off. Our project focuses on the problem with gas mains and the service pipes, and future hydrogen, so it doesn't struggle like the electric network currently is. Hydrogen has about 2.5 times the energy density of methane. So if you burn 1 kilogram of hydrogen versus 1 kilogram of natural gas, you will get 2.5 times the energy. Sounds great, right? But because hydrogen is so much lighter or less dense, you need approximately 3 times the volume of hydrogen as compared to natural gas to get the same amount of energy. So to get the same bang for your buck out of hydrogen as compared to natural gas, you would either need to increase the pressure or increase the volume by installing larger pipes. Due to things like friction, length, diameter, pressure, density, the pressure will drop. So with hydrogen, we need to move 3 times the volume to get the same energy to our boilers. The pipes simply will not cope at peak times, which is around about 8 AM and 5 PM. So to use hydrogen, many pipes may need relaying at significant cost and environmental impact. Boilers use most energy when firing up on initial load, as the red chart here shows. When at the heat, the burners reduce and cycle to maintain temperature. Pressures are maintained as low as possible in the gas network to minimise leakage, approximately 23.75 millibars, so minimal pressure loss is required. So with increased volume required for hydrogen, the pressure loss will be greater and likelihood of boiler failure increased. It should be noted though that due to the density difference of hydrogen, the pressure drop is not linear with volume. For example, the pressure drop over the service is not 3 times that of methane. The boilers will be starved of fuel when trying to fire up and trip out at about 17 millibars. So unless a solution is proposed for the transition to 100% hydrogen, this problem needs solving.
The cheapest and least intrusive way to implement the use of hydrogen for household use is to repurpose the infrastructure already in place for methane. To facilitate this, we propose the use of a local storage of hydrogen in a 2-litre storage vessel, which would activate for short periods when the pressures become too low, as you can see in this photo of the prototype we have made. To refill the storage vessel, a small compressor is used, taking gas at off-peak times, night, or when the inlet pressure is above a trip level. To activate the local storage, pressure sensors will determine when a boost of hydrogen is needed to maintain 17 millibars at the boiler, and the actuator operates valves, releasing short bursts of local storage. In terms of originality, at this time, the closest thing to our product is Boost, which acts like a fan to pull in the extra gas required, but this would cause too many pressure drops on the main infrastructure if implemented widely, i.e. it is not a local store of energy, which is what is needed. Our equipment has been designed to fit the existing meter cupboard, and the costs were included as part of the original paper. As a gas, hydrogen has many safety problems, which are highlighted well in this graph. The y-axis shows how little of a spark is needed to ignite hydrogen compared to the methane used currently, and as you can see, a logarithmic scale is needed to show how easy hydrogen is to ignite. It doesn't take much of a spark compared to methane. The x-axis shows the range of percentage concentration of air/hydrogen mixture for which hydrogen would ignite, again a far wider range than methane. We have thought very carefully about how we can make our product safe, as I will demonstrate, but we focus on our product and its environment, not the wider debate of hydrogen in homes. This will take greater minds than ours. Here are some examples of what we will do. Firstly, all electrical components will be insulated at Apex 2 rating to minimise any chances of sparks forming in the potentially explosive atmosphere. We'll be implementing a solenoid valve connected to hydrogen sensors, which can shut off hydrogen taps as soon as a leak is detected. A pressure relief valve will also prevent overpressurization of the storage vessel. And perforated vents will act as natural ventilation to prevent any buildup of explosive gases. This will help as another safety issue with hydrogen is its flame speed. It expands on ignition 8 times faster than methane, so vents will release this fast buildup of pressure if ignition were to occur.
For the model of the hydrogen canister itself, we had many restrictions to work with. The highest priority one was the pressure it would be stored at, since it needs to be safe, but that is also affected by another important factor, the size itself. Working through many different calculations, we found some approximate characteristics the canister would need. Given that a 2-litre cylinder can fit in a normal meter cupboard, as specified in our paper, it would, at a worst case scenario in which it could provide top-ups running constantly for 3 hours at high demand times, need to be at a minimum pressure of 434 pounds per square inch, or 30 bar. It is important to note that given diversity, it's highly unlikely this amount of hydrogen would need to be stored at one time, given that it can refill in between uses. We believe this value could be safely brought down to below 10 bar, but have currently decided to err on the side of caution with more moles provided. The cylinder will be made of a Type 1 metal hydrogen gas cylinder, which is currently used at far higher pressures than we're proposing for a much longer duration. On this slide are some diagrams I made of a possible cylinder in CAD software. All the measurements are approximate and may have to be adjusted for different meter box configurations, and would be adjusted given more criteria and regulations further along the product design stage. While we focus mainly on how hydrogen could be used to repurpose the existing gas infrastructure, we also briefly looked at how the hydrogen could be sourced. There are lots of sources of hydrogen, but we decided green hydrogen would best fit the fact that this invention is to follow the development goal of clean energy. We looked at using waste electricity to produce this hydrogen via hydrolysis, and would mean the energy wouldn't have to be stored in batteries. And we happen to find that a lot of energy goes to waste via wind curtailment. Our solution will further the development of clean hydrogen initiatives and lessen the reliance on finite resources associated with batteries by enabling hydrogen in homes. Natural gas is a geopolitical fuel due to the infrastructure necessary to obtain and use it, and it is often a tool used in debt trap diplomacy. An example of a current political situation our solution could aid is Uzbekistan's energy crisis, who need to double the energy supply by 2050, and since they're striving to use more clean energy, currently rely on Russia building small nuclear plants in Uzbekistan. Natural gas accounts for over 80% of Uzbekistan's energy supply, and they have a network of natural gas infrastructure that could be repurposed for hydrogen using our solution. It would be cheaper than installing new energy infrastructure, but would still provide new job opportunities in installing and servicing, while still meeting the aim of reducing climate change and emissions. In theory, our solution could be global. Keeping our solution separate from politics, it reduces the opportunity for gas energy to be leveraged in conflicts, meaning constant and clean energy for the people, regardless of any political conflict with their government. To develop our solution into a product that could be implemented in real life, we would need to partner with key stakeholders. The first step would most likely be partnership with gas distribution companies. For our invention to be usable, gas companies could install this equipment now, using methane instead of hydrogen for areas that already experience poor pressure, and by using these live trials, could promote and adjust our solution before expanding it further. We would next aim to partner with boiler manufacturers, ensuring collaboration so their equipment and ours works harmoniously, ensuring seamless transition for customers. We would also need to partner with any agencies or governing bodies who control the standards for gas energy, as we would ensure safety standards are not compromised by our invention. We hope that there's further area for this project to expand to into the future, or that it can at least be open doors to bringing hydrogen fuel concepts into testing and manufacture, instead of just concepts. There are many different methods of transport based on hydrogen that have already been developed, in aviation and heavy machinery, for example, but by providing hydrogen as a domestic fuel with easy access, we hope that there can be a higher uptake on using hydrogen in other mainstream fields like cars. We incorporated an outlet potentially for refueling cars if they can be adapted to work with these conditions. If we can help facilitate hydrogen in homes, then it may act as an enabler for hydrogen in transport too.
Thank you for your time. It was nerve-wracking, but thank you. Thank you to you. It's been great working with you. Are there any questions?
Thank you very much, guys, for your presentation. While I wait for some people to post some questions in the chat or the Q&A, I'll kick off by asking you a couple of questions. Hydrogen is a fantastic concept. I mean, the UK government is looking at hydrogen as a fuel source for heating purposes. And over the next 30 years, one of their ambitions is to see how you can bring more hydrogen into the homes for heating and move away from our sort of dependence on natural gas. But one of the biggest problems with hydrogen is it's a really small molecule, yeah, and so it can leak everywhere. So, I mean, distribution of pipeworks and things like this, how would you envisage the kind of infrastructure needed to develop a pipework network for distribution of hydrogen gas in properties? Do you think that's going to be very expensive?
No, so that's the whole idea of our solution, that we can use existing infrastructure that has been already implemented for methane. So there is no costs whatsoever with relaying roads and implementing new pipes and pipelines to people's houses.
I think to add, ultimately the idea of hydrogen being more likely to leak than methane due to its molecule size, pipes will have worn down over time anyway with use of methane and might need to be replaced anyway. So any of those we would look at replacing with a higher standard, which shouldn't alter cost of replacement far from what they would be maintaining use of methane natural gas. And otherwise, it would probably mostly be on a case-to-case basis when installing within the home if the home's pipework wasn't suitable for hydrogen.
And the other thing is you're going to be looking at changing gas boilers to hydrogen-fired boilers. There's going to be an infrastructure cost there as well. So for people to upgrade their homes to run on hydrogen, do you have an idea of what that would roughly cost them to do?
Yeah, so we worked out the rough cost for each of the modules for the boilers would be about £385 per property, with £15 on average annual maintenance. Obviously, give it 10 years or so, it's likely to need replacing the storage just due to usage. That would vary based on how much it's used. However, overall, we think it's a lot cheaper than, for example, moving to a cleaner thing like electricity, because they cost sometimes up to £10,000 per property. So it should be £385 for this installation, maybe £200 to remove the previous one. Yeah, and then using economies of scale, as if our invention was to be more widely used, the cost would decrease over time using economies of scale.
I think also some boilers are already made to run on blend of natural gas and hydrogen, so it's definitely something that's possible that boiler manufacturers are looking towards, and ultimately replacing your boiler would have to happen eventually. So replacing with a hydrogen one instead of a gas one would hopefully save cost and climate impact for the customer over the future, and is a cheaper alternative to electricity, though what we aim to do is give an energy choice to our customers.
Okay, there's lots of questions posted in the chat. I'll try and work through these. First question, what would be needed to scale this for larger buildings, for example, schools? And just to add on to that, how would you go about having this sort of infrastructure installed in flats, and how safe would that be?
I'm really sorry you cut off on that last bit of the question.
Oh, so how would this work for scale up for larger buildings? And then also, how would this work in properties such as flats? And how would you work around the issues such as safety when you're dealing in houses of multiple occupations or buildings with multiple occupations, such as flats?
Okay, so our product is for when it's working at peak times, which is around about 5 and 8 p.m. So school times would run in between that. So the hydrogen within the mains should be able to cope with the demand from the consumer at that point. But in flats, we're not saying that everyone has to convert to hydrogen. There's usually meter cupboards underground at the basements of flats that we've looked into, so it could still be implemented then. However, due to safety aspects that I'm sure Henry and Elliot will go into in a second, it's probably slightly too unsafe, just as a precaution, to keep them underground. So in that case, in instances, people could convert to 100% hydrogen in those high-rise flats, still again providing them an energy choice.
We did look into high-rise flats, and there are some potential safety concerns, but if it's kept underground, it should be somewhat mitigated, or if stored like outside on the side of the flat. Beyond that, it's possible for some of the larger ones, just for the extra safety, they'd instead convert to all electric. And with more hydrogen, the electric infrastructure would be able to cope with more of this electric. So as a result, then it would bring down costs and also increase the availability of electricity.
Generally, wherever natural gas can be used, our solution would be implementing hydrogen. It would just have to be scaled for different buildings to be suitable for different meter covers or whatever infrastructure they already had.
Okay, there's some more questions posted. I'm going to try and combine some of these together. First question, it says you're talking about hydrolysis as a method for extracting hydrogen. Do you think that's a viable way to do this commercially? And would it produce enough of a high enough yield? Can it be scaled up, basically?
Using just waste energy from wind curtailment for electrolysis from just hydrogen probably wouldn't be able to produce enough hydrogen for large scale if everybody started to convert to hydrogen. Given that most people probably won't do it initially, make that conversion to hydrogen, they'll probably stay on electricity. At the very beginning, we should be able to produce far more hydrogen than we would need for the customers that choose to use hydrogen or a hydrogen blend with methane gas. Ultimately, we would have to draw hydrogen from many different sources, and it would be something that we would look into further when there were more regulations on using hydrogen gas domestically set by governing bodies.
Okay, one other question. This is from Peter Davidson here. You say that one needs 3 times the volume flow of hydrogen, but the density of hydrogen is 1/8 that of methane. So if the increase in pressure drop is due to the pressure drop only, what's this, RO? Sorry, Peter. Drop due to ROU2? I'm sorry, I don't know. Oh, you're gone on mute again. Sorry.
The pressure drop's due to a half rho U squared.
Yeah.
It's Darcy's law. So if the density goes down by a factor of 8 and the volume flow goes up by a factor of 3, does the pressure drop actually increase that much? So if you think of the product,
mental arithmetic is not quite there yet. We think that the pressure drop over the surface would be about 5 millibars. So that's what most.
Well, wait a minute. You've all done A-level maths, I think. So you've got rho u squared is the pressure drop. Yeah. Okay. So what you've said is that the velocity goes up by a factor of 3. So u increases by a factor of 3.
Yep.
Yeah. So u squared is going to go up by a factor of 9. But the molecular weight of hydrogen is 2. And the molecular weight of methane is 16. So the ratio of density is a factor of 8. So 9 over 8 is only a small fraction.
Yeah, and yeah, obviously it is very minor, but at the moment there are already some issues with pressure drop, which is why our product is needed in this field, because at the moment they're using things like Survey Boost to pull the extra air out. If we did that with more wider scale, it would cause an increase in the hydrogen being pulled out, which would decrease the pressure too far. So because the pressure drop hasn't decreased enough, this product is still needed, even though it's not massively increased, it's only a small increase.
Okay, I can see there's lots more questions posted here, and there's some more in the Q&A, but we've got to move on. So I'm going to wrap up with one last question. How do you plan to combat public skepticism given the associated risks?
Well, obviously, hydrogen is a very controversial topic, should we say, after Hindenburg and the H-bomb. So it's something that needs the public to be more informed about the positives of hydrogen, because even methane, which is used at the moment, can be explosive. So it is just ensuring that it's safe, and then it's informing the public of all the positives. In a survey by the UK energy company, I think it was, they did a survey between -3 for strongly disagree and 3 for strongly agree, and the average of the population was 0.81. So it shows there is a long way to go, but it's currently not in the negatives. So I think with enough political opinion and with more of these products being rolled out, eventually we can get that further up and make hydrogen more widely used.
I think when you familiarise people with something, they become more aware of the positives and less about the dangers of it. Lithium-ion batteries can be very dangerous, but it's something that we're all very used to in everyday items. And I think informing people about the safety measures that we'll take will help sort of eliminate worries, perhaps.
Okay, brilliant. There are many more questions here, and I could see some of your competitive team. They are eagerly posting questions, but I'm going to have to move on because of time. Thank you very much. Well done, guys. So we're going to move on to the next team now. Thank you, guys. So we're going to move on to the next team now. Breaking Bonds. Please come online. Okay, do you want to share your screen? Make sure you unmute as well. That's it. Yeah.
Yes, just a second, please.
Yeah, we can hear you. Yeah. Do you want to put it into presentation mode?
Yeah.
Yeah, we can see your slides. Ready when you are.
Hello and welcome to our presentation on the removal of per and polyfluoroalkyl substances from treated water. Having only finished GCSEs yesterday, we are really excited to share our ideas, and we hope you enjoy the presentation.
With clean water and sanitation as our targeted sustainable development goal, we propose a 5-step solution beginning with the quantification of PFAS through combustion ion chromatography, the absorption of PFAS to nanoparticles, the microfiltration of the nanoparticle PFAS compound, and finally, the complete degradation of PFAS through boron nitrate bore mining.
As it currently stands, British water companies are unable to effectively remove PFAS during potable water treatment. thus meaning that every glass of water we drink likely contains PFAS.
Therefore, we propose adding a new processing stage between filtration and disinfection, which aims to thoroughly clean our water, cultivating a healthier future for all.
Consisting of 4,700 molecules, PFAS is a family of man-made substances consumed both industrially in the manufacturing of aerospace, automotive, and electronic materials, as well as domestically in the innocuous items of non-stick frying pans and nail polish. Their dual hydrophobic and hydrophilic properties make them water, oil, and stain resistant, while their unreactivity enables them to poison our planet for millennia without degrading.
The danger of PFAS lies in its invisibility and longevity. Odorless, colorless, and unreactive, the carbon-fluorine bond of these forever chemicals enables them to accumulate in dangerous quantities. Consumption of POFA, a type of PFAS, causes an increased risk of testicular, liver, and kidney cancer, while the bioaccumulation of PFAS harms the ecosystems and the planet.
Neglect, coupled with the lack of awareness surrounding this pertinent issue, has enabled PFAS to percolate water supplies through landfill leachate, industrial emissions, and firefighting foam. The Royal Society of Chemistry found that over one-third water sources in England and Wales exceeded the safe limit of 10 nanograms per litre, while the Environment Agency detected PFOA, a type of PFAS, in 1,000 water sources between 2006 and 2022, with the highest concentration being 149 nanograms per litre.
This map shows the prevalence of PFAS in Europe, with the red dot indicating areas where PFAS has exceeded the safe limit. Thus, we propose our solution.
Stage 1 is the quantification of PFAS present in water following filtration. PFAS contains a carbon-fluorine bond. Thus, if the mass of fluorine detected exceeds standard levels, PFAS is present. Combustion ion chromatography can be used to determine adsorbable organic fluorine in aqueous samples. A water sample is oxidized through pyrohydrolytic combustion under a humidified argon or oxygen atmosphere at 1000 degrees Celsius, and the released vapors are absorbed into an aqueous solution to be converted into halide and sulfide ions. Subsequently, the water sample is injected into an ion chromatography system where ions are separated based on different affinities to the analytical column. A conductivity detector quantifies PFAS through comparing the intensities of detected measurements with those of certified calibration standards.
We also explored using liquid chromatography mass spectrometry, as it is a good separation technique for larger, non-volatile molecules with a broad sample coverage, but decided that CIC was more industrially feasible.
The adsorbable organic fluorine concentrations measured can be used to calculate the mass of the nanoparticles needed to absorb the PFAS molecules in the next stage.
Using the programming language Python, we developed a code that calculates the amount of nanoparticles needed to absorb PFAS for the purpose of filtration. The user inputs the volume of water and the measured concentration of PFAS, which is the initial absorbent. A function representing the displayed equation calculates the adsorption capacity of the nanoparticles in proportion to the PFAS concentration and rounds the output to 3 significant figures. It returns it to the user, who then releases this mass of nanoparticles into the water. If the PFAS concentration was less than or equal to the safe level of 10 nanograms per litre, the user is informed that no action is required. For example, if the user inputs the concentration of PFAS in the water as being 60 nanograms per litre in 1 litre volume of water, the expected output of the code should be 500 milligrams of nanoparticles to be released.
Stage 2 involves adsorbing PFAS molecules to nanoparticles. Adsorption refers to the attachment of liquid or gas molecules, the PFAS adsorbate, to the surface of a solid, the nanoparticle adsorbent. There are 2 types of adsorption, physisorption and chemisorption.
In physisorption, weak van der Waals forces attach the adsorbent to the adsorbate, forming a non-specific outer sphere complex with an adsorption heat of 20 joules per mole. The low binding energies of van der Waals forces mean that physisorption is faster, occurs at lower temperatures, and is reversible, hence why we are using it to adsorb PFAS to nanoparticles.
Chemisorption, however, involves strong covalent or ionic bonds between the adsorbent and adsorbate. Forming inner sphere complexes at high temperatures with a high enthalpy, chemisorption is irreversible and thus unsuitable.
In our research, we evaluated metal oxide and carbon-based nanoparticles, ultimately choosing granular activated carbon, as its hydrophobic properties enable it to adsorb high polarity, long-chain PFAS, like PFOA.
Additionally, we will use bioadsorbent nanoparticles to target low-polarity short-chain PFAS left behind by GAC as part of a 2-stage system, ensuring PFAS of all chain lengths is absorbed. Economically and environmentally sustainable, GAC is sourced from wood and coconuts, while bioabsorbents are derived from biomass feedstock like non-woody plants.
Programming in Python, we created a simulation of the adsorption process, with the blue molecules representing the PFAS and the green molecules representing the nanoparticles, in order to visually demonstrate the mechanisms of our previous code.
So as you can see here, this simulation just represents the absorption process. The code we previously showed will calculate the amount of nanoparticles to be released, and that's what will happen in the water supplies. So, stage 3 involves filtering out PFAS nanoparticle compounds through a membrane of pore size 0.1 to 10 micrometers. Cost effective when able to remove a wide size range of nanomaterials, microfiltration is optimal as GAC and bioabsorbents are differently sized.
Stage 4 is the regeneration of spent nanoparticles. As physisorption is reversible, thermal desorption separates the PFAS nanoparticle compound by heating it to 400 degrees Celsius and absorbing the PFAS released from nanoparticle surface into fluid/vacuum. The spent nanoparticles are collected, heated to 500 degrees Celsius, volatilizing any remaining absorbed material, and reactivated with steam. 5 to 10% of carbon is lost each time, but this can be supplemented cheaply.
Stage 5 is the degradation of PFAS through boron nitrate ball mining. This involves grinding PFAS molecules with metal balls at high speeds, creating collisions between the balls and additives that degrade the carbon-fluorine bond and convert it into innocuous products. Potassium hydroxide is the conventional additive used. However, we propose replacing it with boron nitrate, a non-corrosive, cheaper alternative that degrades fluorine atoms in just 4 hours.
The originality of our solution lies in the creativity and ingenuity with which we combine existing techniques, creating not a physical product, but a unique methodology. Using GAC and bioabsorbents in conjunction to absorb all PFAS of all chain lengths, as well as degrading PFAS through ball mining instead of incineration, the conventional method, distinguishes our idea from others regarding this issue. Furthermore, our utilization of computer programming enables us to automate the process efficiently, blending fundamental scientific principles with technology to advance the future of water treatment.
Throughout this process, we have aimed to optimize costs to ensure economic sustainability. CIC was the cheapest method of quantifying PFAS concentrations, as the equipment is durable, maintainable, and priced as low as £6,218 from Metron, a Swiss company. CIC's simplicity eliminates the need to hire specialized technicians, further reducing costs.
Furthermore, both GACs and bioabsorbents are sourced inexpensively, with GAC costing between 39 to 79 pence per 1,000 gallons, while the regeneration of spent nanoparticles is also cost-effective and industrially viable.
Socially and scientifically conscious, we aim to promote the fundamental human right of access to clean water, which underpins our strive for sustainability. We hope to establish peace in ensuring that everyone has access to clean water, while creating trustful partnerships between local communities and water companies in an effort to improve the health and prosperity of the people and the planet. Here are our references for everything we've researched. Thank you for listening, and we are now open to any questions.
Thank you very much, guys, for a fantastic presentation. Well done. I can see there's a question posted already here. This is some ego questions coming through. So first question in the chat says, what are the safety implications of the carbon-fluorine bond in PFAS, and how have they been tested to prove they will not form fluoride radicals which damage ozone?
So the implications of the carbon-fluorine bond are that it makes it very unreactive, which means it's quite difficult to target with conventional water treatment processes. That they can last for about 1,000 years without degrading, and the carbon-fluorine bond also gives them many properties. For example, it's both hydrophobic, attracting water, and hydrophobic, repelling water, and hydrophilic, attracting water. So it just makes it a very difficult molecule to deal with, hence why it's been such a difficulty trying to get rid of it in previous decades. The second part of the question asks, how can we prove there won't fluoride radicals? So as far as we're aware, boron nitrate ball mining aims to entirely degrade the carbon-fluorine bond and convert it into innocuous products. In our research, we also came across using, I think, electricity or electrochemical, some kind of electrolysis and able to fully break down the bond. And that is also like a viable method, which I think is entirely safe as no radicals are formed. However, it was very expensive and quite complicated. So we didn't think it was really something we could implement industrially on like a global scale. So that's why we went with boron nitride ball mining instead.
Okay, another question that's come up in the chat. What would be the working cost of this? What would be the cost of heating to very high temperatures multiple times? Would this be economically viable, especially with regards to scaling it up?
So we do believe that this is economically viable as the temperatures involved aren't necessarily too high. That we talked about physisorption for absorbing the nanoparticles for absorbing PFAS, the nanoparticles, and this only involves heating it. It has a very low absorption heat and a very low enthalpy. So it only involves heating it to quite relatively low temperatures. I think the maximum we at least discovered in our research was about 400 degrees Celsius. So we believe many industries involve like in heating materials to such high temperatures. So we believe that this isn't entirely out of reach. And we believe with combustion ion chromatography as well, we believe that's quite like a simple method of identifying PFAS, and it also doesn't really involve heating it to that high temperatures. The regeneration of nanoparticles is where I believe the highest temperatures are involved. I think when heating the nanoparticles to about 500 degrees Celsius to volatilize any remaining absorbed material, that's where the issues may come into play. However, we do believe that other industries have, 500 degrees Celsius is an achievable temperature to reach, and also the regeneration of nanoparticles makes it a lot more sustainable in the long run. So rather than continually buying more nanoparticles, simply heating it to about 500 degrees Celsius once or twice is a lot more economically viable than continually replacing them.
Okay, questions here. What about the effects of contaminants such as humic acid on the absorption process? Could this clog up most of the absorbents?
So we aim to implement our technology, well, not technology, we aim to implement our process following filtration. So we hope that by that point, some of these, so we're trying to find the question again, I do apologize.
So the question is, yeah.
We do believe some of these contaminants would have already been filtered out. If not, during absorption, the PFAS and like after absorption has already occurred, we don't believe this would impact absorption. But after the PFAS and to nanoparticle absorption has already occurred, during thermal desorption it's heated to quite high temperatures. So we do believe that these contaminants will be destroyed like in the process of thermal desorption. So it shouldn't really affect it either way. However, we haven't entirely researched that yet, so I can't give a definitive answer on that. But I don't think we should plug it up.
All right, just a follow-up question from that. And there's a lot of water treatment works already have GAC. Have you looked at how much PFAS are currently removed, and if your process would remove more? How does what you're proposing going to be a step change to processes that already exist to remove PFAS?
So GAC, as you're right, has been around for a very long, like it's frequently used in water treatment. However, they use GAC filters. We're using GAC nanoparticles. That's where the difference in us lies. We, as far as I know, are some of the first people to kind of use GAC nanoparticles in the filters. And GAC is actually very effective with like PFAS like filtration already. But I don't have a definitive number or percentage to kind of give on this. But in our research, we did find that they are very effective, and that's why we decided to use them as well. So we do believe that because we're also using bioabsorbents as well as GAC is very good at absorbing long chain length PFAS because they have quite a high polarity, but they're not really good at absorbing like PFOA, for example, but they're not very good at absorbing short chain length PFAS. I don't really have an example for that, but we're using bioabsorbents as well to kind of target the PFAS left behind. So we do believe, like, because we're not just using GAC, we're using both of them together. So overall, this should be able to target PFAS of all chain lengths. So because GAC is already effective and bioabsorbents will kind of just help it out where it fails, we do believe that it should all be very like efficient and everything should be absorbed all together.
Okay, final question before we move on. Is the absorption process equilibrium or diffusion limited? And did your Python model account for this?
So the absorption process we're using is phase absorption, and this is equilibrium limited. I'm not sure. We showed an equation on the slides with our Python model that I think we sourced it from isothermic kinetic studies. And so yeah, that one of the inputs of our one of the inputs that the Python code uses is the actual equilibrium value itself. So it is equilibrium limited, and we did try to show this in our code. However, it was quite brief, so maybe it wasn't really properly displayed. But thank you.
Thank you.
Brilliant, guys. Well done. Well done. Thank you so much for your talk and working through the questions. Okay, so we're going to move on to the next team, our final Team Mozo. Team Mozo, would you like to come online? Hello, we can hear you. Would you like to share your slides?
Yes. Sorry, just hang on. Okay. Can you see that okay? I think it's just loading.
Yep, your slides are up and we can hear you fine.
Okay, perfect.
Nearly 500,000 people died in 2022 due to malaria. We are Team Mozo and our aim is to reduce this. Malaria is an infectious disease caused by Plasmodium parasites and transmitted using female Anopheles mosquitoes as a vector. According to the WHO 2023 report, cases are on the rise, with an estimated 249 million malaria cases globally in 2022, which resulted in 426,000 deaths, exceeding the pre-pandemic level in 2019 by 16 million cases. Pyrethroids are the most common chemical ingredient in modern insecticides. The rising resistance to pyrethroid-based insecticides in recent years means that a sustainable, non-bioaccumulating solution needs to be found to malaria vectors. A family member of mine recently contracted and recovered from malaria, so this issue couldn't be closer to home. Our project focuses on tackling SDG 3 to ensure good health and well-being. We specifically look at the target to end the epidemic of malaria, among other communicable diseases, by 2030. To achieve this, the WHO has set the goal of reaching 6 or fewer malaria cases per 1,000 people globally in 2030 under SDG 3.3, an aim that our product helps to address. By focusing on the sustainable production of our invention, we hope to also consider SDG 12, ensuring efficient use of materials and less waste.
We have come up with a product which acts as a mosquito trap to be attached to a window or a light bulb. It specifically targets the malaria vector, Anopheles mosquitoes. It consists of 3 main parts working in tandem: a dispenser soaked in a chemical-based attractant, a plant-based biosurfactant to drown the mosquitoes, and a biodegradable main body. The only existing product that we are aware of that has created a mosquito trap without the use of carbon dioxide is Biogens, which still relies on a power source to kill the mosquitoes, and also targets Aedes mosquitoes as opposed to Anopheles.
After the initial ideas were developed, I took on the role in creating the mosquito trap design. We looked at past designs which used ultraviolet lighting and took inspiration from the shapes that combine both attracting and trapping the mosquitoes. As our project continued, we came up with the numerous designs, however settled on the design as shown. As you can see, the design is compact, fitted with a nylon strip and a basin which contains the surfactant. With these 2 features, the mosquitoes are attracted to the nylon strip, where they enter the valve-shaped funnels. The funnel feature ensures that the mosquitoes can easily enter the trap, however find it hard to exit the trap, resulting in a higher chance of killing the mosquito. Once the mosquito has entered the trap, they then land on the surfactant, where they drown and fall to the bottom of the basin. Over the time, the trap will collate dead mosquitoes, where the user will then unscrew the basin from the top section, and then we'll be able to use the sieve to filter the mosquitoes from the surfactant. This is done through pulling the cylinder-shaped handle upwards. We implemented this to ensure that there will be limited waste from each mosquito removal. After around 40 days, the user will then be advised to change the nylon strip. The nylon strip has been designed so that it can be mass-produced but also easily replaceable. This is done through detaching the top and bottom section, then undoing the screw from the top of the trap, which means the nylon strip can be removed. This process can be repeated each time the user receives their newest strip.
In order to attract the mosquitoes, we have looked into a range of chemicals. One blend consisting of octanol, acetone, decanol and nonanol has been found to act as an aggregation pheromone, being released by males during swarming and acting within a short-range distance. Another blend, which we found to be more practical, uses cyclopentanone as an attractant. This removes the need for carbon dioxide, as a chemical binds to and triggers the same receptors on the maxillary palps of the Anopheles mosquitoes as carbon dioxide. When 3-methyl-butanol is found from the human skin microbiota is added, the attractiveness of the existing blend has been found to increase. Existing studies have looked at nylon strips as a dispenser for chemical attractants, which are found to be effective around 40 days after first soaking. We seek to use a starch-based bioplastic as an alternative, as it is biodegradable and has potential to have a longer efficacy. When considering the safety of the attractant, we need to consider the potential skin and eye irritation if direct contact is made with cyclopentanone or the methyl-butanol. We saw during testing, using both nylon and bioplastic, that the dispenser needs only be soaked in very low volumes of the chemicals, which should mitigate this problem. Both chemicals are found to also to be biodegradable in soil, allowing for easy disposal.
When considering how to dispose and eliminate the mosquitoes, we researched using an adhesive trap, electrocution, and crushing. However, due to limitations, including a power supply and disposal, we decided on drowning. By using a surfactant in water, its surface tension would be reduced below that required for a mosquito to land on the water. A surfactant works by disrupting the hydrogen bonds between water molecules that arise due to its polar nature. A surfactant has a hydrophilic head, attracting polar water molecules, and a hydrophobic tail, which repels the water molecules. The advantages of using a surfactant include its reusability, sustainability, and independence from an energy supply. A surfactant we believe would be suitable are rhamnolipids produced from bacteria. The surfactant reduces the surface tension from 72 millinewtons per meter squared to 30, a value low enough to wet mosquitoes flying or resting and make them fall. One limitation of using a surfactant is that some liquid will be lost every use, and thus new surfactant will need to be added every 2 months. However, we predict that only 2 millilitres of water will be lost per use. During research, many companies already use surfactants in mosquito traps. However, very few consider the environmental impacts of their use and production, making our trap unique. When considering time and cost, which is covered later in our presentation, we realised that injection moulding would be a more advantageous manufacturing method. A sustainable thermoplastic we found suitable in research was PBAT. It is a compostable biopolyester obtainable from renewable resources. PBAT biodegraded by over 80% within 45 days in a test carried out by the Testing Institution of Organic Waste Systems. Whilst our product is in use, it is important that the main body does not biodegrade. A study we found showed that soil biodegradable PBAT and compostable PLA mainly went through photodegradation in air and only lost 1.1% and 0.8% in weight after 6 months, respectively.
Our product has environmental issues and sustainability integrated throughout its design to ensure it satisfies SDG 12. This is demonstrated in the product not requiring a power source or carbon dioxide canister and being based out of biodegradable materials. The PBAT bioplastic used for the main body is better than PLA, which means it in an industrial composition to break down. With PBAT on the increase and expected to quadruple in manufacture in the coming years, it will be more readily available, therefore not only cost less, but have lower transport emissions due to being more widely available material. In order to gain an understanding of how much our product may cost, we created a spreadsheet in which analyses both the implementation cost of the product and the annual cost. The price per product could be reduced by presenting the user of the product with the option to use their own surfactants, such as a plant or animal fat-based soap. This would also lower the environmental cost and impact of the product. We evaluated the cost of the product to be £3.29 initially, and with a £16.93 annual payment, the initial cost is 300% cheaper than the price of the mosquito trap BG Sentinel, making our trap more accessible.
We tested our initial prototype model in Sri Lanka, leaving it near a lake which is a known breeding ground for mosquitoes. We made both nylon strips and a starch-based bioplastic from acetic acid to act as dispensers, and soaked them in methyl butanol. Whilst no mosquitoes were found after 2 hours, we identified the mosquito coils, which were placed very close by, as being a likely issue in our experiment, counteracting the effect of our trap.
To test our third prototype, we left the product near a water body in a local woodland for 24 hours with a control experiment of our second prototype with no chemical attractant. Both traps were placed at opposite ends of the water body, such that it experienced equal sunlight, humidity, and temperature. Our trap with the chemical attractant caught 22 insects, whereas the trap without chemical attractants only caught 3.
Our trap works towards the 5 Ps of sustainable development, by providing a trap which saves people's lives while minimising any harm to the planet. It encourages prosperity among communities by reducing the burden on healthcare systems, and looks for partnerships between communities against a common problem.
With more research and time, we would like to look into different dispensers which are effective for longer periods of time. We have also looked into using LEDs emitting specific wavelengths of light to enhance attraction. Another idea we had was to install a fan to the trap to help increase circulation of the chemical attractant smell. This would all be solar powered. In summary, our trap is a sustainable, mass-producible, and easily accessible design to tackle rising deaths from malaria in accordance with SDG 3. Whilst looking at production, we have tried to keep in mind SDG 12.5 to minimize wastage and ensure responsible management of resources.
We'd like to thank the Chemical Engineering and Biotechnology Department at Cambridge University, as well as the Association of Science, Technology and Innovation and the Institute of Chemical Engineers for running this competition. It's helped us develop our interest in chemical engineering and certainly inspired us to learn more about this discipline. We'd also like to thank our DT, Physics and Chemistry department, especially Mrs. Cannon, our legendary chemistry technician, for helping facilitate tests of our products. Thank you.
Brilliant, guys. Thank you so much for your talk. I can see there's a couple of questions posted in the chat, but while we wait for some more to come in the chat, I would like to start by asking a couple of questions to you as well. So you're talking about adding some sort of a chemical to the nylon to attract mosquitoes, such as a combination of different types of solvents, such as acetone and such. How long will that last? Would that not just all evaporate?
So we found in studies that have previously used these kind of chemicals as attractants that they last for 40 days using nylon strips as a dispenser before they have to be replaced. So again, we would want to conduct our own test with this, but based on previous information, we would say 40 days is what the current efficacy is.
And the other question I had is again about consumer behavior and users. I mean, this requires the users to load up the nylon with a combination of sort of a cocktail of solvents for attracting them. You've also got to think about adding a surfactant to the water. Can you envisage user experiences being a hurdle in your design, in your concept?
I think that's definitely something we would like to consider if this were to be scaled up to a larger scale. However, we think that, we'd like to optimize that our product is kind of as straightforward as possible. So for example, with the PowerPoint and changing the nylon strip, we'd like to probably, if we were to release this commercially, we'd like to offer a manual and also spend more time in optimizing that kind of replacing system and making it clearer for those users. But that's certainly something to consider.
And also to add to that, in terms of the chemicals, we are using the chemicals that we conducted the most research into and found to be more practical were cyclopentanone and the methyl butanol. And both of these are actually currently used in the manufacturing industry as flavorings in food and also in perfumes. So users will have frequent use of these chemicals. So worry about them shouldn't be a problem, given that they're exposed on a frequent basis to them.
And to add on to the customer experience, the nylon strips will be like a monthly subscription where they'll be able to be replaced and sent back to help with environmental recycling and to make sure that it's easily accessible for the consumer to replace.
Good. Okay, there's lots of questions posted. I'll try and combine some of them. Have any of the tests on the equipment been successful with mosquitoes to date? And in the tests you're doing, were there only mosquitoes that were trapped or any other types of insects that were trapped?
So for the tests we carried out in the woodland, we didn't identify the species that we did trap. And I guess that kind of brings in consideration of the kind of impacts on the ecosystem. However, we'd like to think that these traps would only be used in more urban, well, still in problem areas, but in specific scenarios, so in rooms and stuff, where they wouldn't damage the ecosystem as much. So again, we didn't identify these species. However, with further testing and more time, we would like to take more consideration into what kind of species end up being trapped and killed in our trap.
Yeah, but obviously due to our attractant being targeted specifically at Anopheles mosquitoes, we would hope that the majority of the insects trapped would be Anopheles mosquitoes, given that it's specific to them.
Okay, another question. LLIN's long-lasting insecticidal nets are usually the most cost-effective way of controlling malaria. How does your dispenser compare to that?
So I think one of the problems we encountered with these nets is the emerging resistance to pyrethroids, with the mosquitoes getting mutations, which means the pyrethroids aren't able to disrupt their nervous system. So the pyrethroids and the insecticides and the nets as a whole are actually becoming less effective. Also, the WHO has released data on disposal of these nets and found they recommend that the nets are burnt, which obviously has a big environmental impact. Yeah.
Which is another limitation of those nets.
Okay, another question. How would these attractant chemicals be sourced? Would these not have to be derived from crude oil sources, and how would this be economically, environmentally sustainable?
So these chemicals are, I think, as I previously mentioned, they're used a lot in the manufacturing industry at the moment as flavorings and in the perfume industry. So they're already mass produced. So that sourcing the chemicals shouldn't pose a massive problem.
In regards to the environmental issues, we didn't include it in our presentation. However, we also looked into, we found a few studies suggesting that human sweat was also quite a good attractant. So with more time, again, we maybe would like to carry out some testing using human sweat as an alternative, I think.
Okay, I think we will wrap up here. There's lots more questions in the Q&A section. So without any further ado, I would like to pass on to Gavin Patterson, and thank you so much for your time today, Gavin, and over to you.
Well, thank you very much, Cameron, and good to see Peter as well. Your father was head of the department when I was there, so I remember him very fondly, and I had many happy days there. So I've been asked to talk a little bit about my own career over the last, I guess, 35 years or so, since I was at Cambridge. I went to Cambridge in '86 to 1990. I'd gone to a comprehensive school in Somerset, and came up to study chemical engineering, was sponsored by ICI, which I had Peter, of course, referred to Billingham, which made me smile, which is where I spent many happy summers. I had a fantastic time at Cambridge. I was at Emmanuel College. I think it's fair to say I wasn't remembered for my fantastic academic achievements, but nonetheless learned a great deal, made many great friendships, and the 4 years I spent in Cambridge really set me up for the rest of my life. So as you're thinking about it, if there's one thing to take away from today, I strongly encourage you to think about applying. It's a fantastic experience, and one that will hold you in great stead the rest of your life, regardless of what you choose to do. In terms of my own career, I intended to be an entrepreneur and start my own business, because I had my own business while I was at Cambridge as a little side hustle. But as my life has turned out, it didn't actually work out that way. Once I left Cambridge, I wanted to run my own business, as I say. So I decided I'd better go to a company to learn how to do that. And in those days, the place to go if you wanted to learn how to run a business was P&G, Procter & Gamble, where I spent the first 9 years of my career in brand management and marketing roles across the UK, Europe, and indeed around the world, working mainly on hair care brands. My chemical engineering experience held me in great stead, because there were, in spite of being on the brand management side, I had a strong understanding of how to make things, which was extremely useful. In the sort of late 90s, the internet was really taking off, which will be a surprise to many of you, I guess, today. These were the days before everybody had mobile phones and continuous access to the internet, but it was really taking off. And I decided to change course and enter what is known as TMT, Technology, Media and Telecommunications. In some ways, I chose the wrong T. I chose telecommunications, which if you'd have chosen technology in those days, I would have retired a lot younger than I actually ended up doing. But nonetheless, I had an incredibly fulfilling career, initially in what's now Virgin Media for 4 years, and then 16 years in BT, including 11 on the board, and 6 as the chief executive between 2013 and 2019, and got involved in some really interesting projects. We were right at the forefront of rolling out fibre, and now rolling out full fibre. We acquired EE and created a fixed mobile business that is the market leader in the UK. We got into cybersecurity, did a lot in corporate social responsibility, got into sports broadcasting, which was and launched BT Sport, which is a very exciting initiative. And I had a fantastic time. By early 2019, having done 6 years, I stood down, and I wasn't sure what to do at that point, because I was still relatively young. I was 51, and I then sort of concluded that I needed another executive job, and quite fortuitously, an opportunity arose from just a relationship I'd built up over the years. I knew the CEO and founder of Salesforce, and he invited me to become the Chief Revenue Officer. And that was a great 3-4 years, in fact. I moved to San Francisco. I learned a new technology, a new business, and in spite of COVID, the business flourished and almost doubled in size in that period. And most importantly, I learned a new business area, learned about technology and how software in particular and SaaS platforms could really transform any business that you want. So ultimately, it was never going to be a long-term move for me. I wanted one last gig, as it were, and so in early 23, I decided it was time to retire properly. And since then, I've been developing a portfolio of non-executive directorships and advisory roles, but also some not-for-profit jobs as well. And I'll talk a little bit about the importance of those. So these days, I I sit on a couple of public boards. So Wix, WIX, which is the market leader in online cloud-based website development and e-commerce, that's listed in the US. Ocado, which is also a technology company primarily, but also has a joint venture with Marks and Spencer's in food retail in the UK, but supplies 13 companies around the world with world-leading robotics in warehousing. A very exciting UK world leader. And then I do a lot these days in with private businesses, some startups that are really just entering the market, but primarily with scale-up software businesses that are backed usually by private equity. So those include Chair and Kahoot, which is, I'm sure many of you know, the world leader in tech ed gamification of content. I'm sure most of you have used it in one form or another. I chair Kraken and advise Octopus Energy, which is a fabulous business, only 8 years old, founded by 3 Cambridge graduates, and is driven fundamentally by software. And that software platform, Kraken, is being rolled out to energy companies all over the world as well. I sit on the board of Beamery, which is a talent management platform. I also sit on the board of Molt. I chair a business called Elixir, and I think that's mainly all I do. So they're mainly software businesses, and I've got increasingly involved in software as I've seen the potential of software as a way of transforming any organization. I've also, throughout my career, continued to do things on the not-for-profit side and around education. So I sat on the board of the Judge Business School for 3 years. I was a trustee at the British Museum for 8. I chaired business in the community for King Charles. And I sit on the board of the London School of Economics and Political Science these days, which is very interesting. But I've found that being on not-for-profit boards and being in on the boards of universities or educational establishments like the British Museum, extremely rewarding. You meet a completely different set of people than you meet in the business world, who often tackle problems from a fundamentally different perspective, and that really stretches your mind and keeps you on your toes and helps you to continue to learn, and that's a theme I'll come back to later. So that's my career in a nutshell, and I probably just wanted to reflect in closing on, I think I've written down 5 lessons or observations, if you like, reflections of my career and what it's meant for me, and hopefully they might be useful to you. I think the first one is I strongly encourage you to apply to the chemical engineering biotechnology course at Cambridge. It is a very sought after degree in the job market, and adding biotechnology is an inspired build on the course that I did when I was in Cambridge. It teaches you how to think. There's no better way of putting it. The robustness of the thinking process helps you with any strategic problem that you come across. It helps you with creativity, it helps you with conceptual thinking, and that you can apply to not just chemical engineering jobs or vocational jobs that come out of chemical engineering, as you can sense from my own career, it's allowed me to move between different organizations, different types of business, different markets, and be able to pick up and hopefully make a contribution relatively quickly. And that in itself, I think, is extremely valuable. So, many of you, I think, will end up working for 50 or 60 years, and to do that, having a great foundation is critical, and the degree that we're talking about, the chemical engineering biotechnology degree, I think really will give you that. I think the second thing I would say to you, and as you go through life, this becomes more and more important. Your relationships matter. So the friends that you're making these days at school, you'll make, if you apply and get in, you'll make some amazing friendships in Cambridge. But then throughout your business life, they are absolutely critical for you making your way through life and making the best of it. Life is difficult at times. You need to rely on people. You need to be able to inspire people to get things done in your job, but you also need their support and advice, in the good times as well as the bad times. And so I strongly encourage you to, whatever you're going to do in life, make sure that you continue to replenish the relationships you've had or you have, because they'll last you a lifetime. And the friends I met in Cambridge have very much done that for me. And indeed, even a week ago, we were going away together. We went away together for a trip and reminisced about our time together. And they've been an immense support to me as I've gone through life. So I really encourage you to make sure you look after your friendships and your relationships, not just with your friends, but with your family as well. I think the third thing I would say is commit to a lifetime of learning. I was blown away by your presentations today, truly inspired. I was out of my depth at times understanding them, and I was certainly impressed. And congratulations to all of you, regardless who wins. But if you keep a commitment to lifetime learning, stay curious, stay relevant, you'll find yourself, I think, having a more fulfilling life and being able to make a contribution to society for longer. And I'm certainly finding that as I'm in my mid-50s. The key to remaining relevant is to keep learning and really pushing yourself. And as every new technology comes along or new concepts, try to stay on top of them and try to continue to learn throughout your life. One of the reasons I've done non-executive roles in education is exactly for that. It's making sure that I continue to stretch myself, and I'd really encourage you to do that. I think the fourth thing I would say is life is about taking risks, and it's about courage. If you want to live a full life, in my opinion, you've got to take some risks along the way. Doesn't mean taking risks constantly. It means taking calculated risks. It means, following your instincts and intuition at times, but not being afraid to do something different and to push yourself. And particularly in your 20s, I think this is really important to try new things and really get to know yourself better. I don't think I really understood who I was and what I wanted to do with my life until I was towards the end of my 20s. And you don't come out of university a finished article, even if you're classified as an adult, I guess, at that stage. your 20s are times to try new things. Risk, of course, is both a positive thing and a negative thing, but getting a good, getting confidence in being able to balance those risks, and making sure that it is something you can live with the consequences regardless of the outcome is really important. And related to that is decision making. The further you go through life in your career, one of the things that differentiates you and distinguishes you is your ability to make decisions, good decisions, of course, but to make decisions efficiently. You don't need to make every decision and get it right. You've just got to be able to make them quickly and get most of them right. And when the facts change or you learn something new, you've got to be able to course correct. But the one thing that does stop you is procrastination and an inability to make decisions. The people around you can't function if that's the case. So really building the confidence to back yourself and take choices and be courageous in those choices is something I would encourage. And then finally, think in a 360-degree way. Use both the left side of your brain and the right-hand side of your brain. In simple terms, the left side is logic and rationale. You'll learn that. You probably learn that. There's no better place to learn that than in Cambridge, I think. To be able to think in a logical, analytical way, I think, is one of the things I certainly took away. But you have to be able to use your instinct as well. And that becomes more and more important as you go through your career, and be able to understand what that instinct is telling you, and then rationalize it, but be able to have the confidence to use all aspects of your thinking process rather than simply working on an analytical way. Why is that? Because often you need to make judgments and decisions based on people, and sometimes it's based on what your instincts are around that person and whether you can trust them and rely on them. And if you don't hone those abilities in your earlier stages of life, it's quite difficult to acquire them at a later stage. So those are my thoughts. I mean, in summary, congratulations today. I thought they were amazing presentations. Sadly, there can only be one winner, and you're about to find out who that is. Have a fabulous life. Look back on your life, and I wish when you do that, it is a life well lived. Thank you.
Thank you so much, Gavin, for your very nice talk, and it's very insightful talk of all the interesting opportunities you've had in your career. It's really motivating to hear all these things. Okay, so I'm now going to pass over to the IChemE President, Mark, who will be announcing the winners.
Thank you, and thank you for inviting me along. And I think just wanted to echo some of Gavin's words there in terms of what an inspiring way to end the week, and hear all of the great work that everyone's been doing in this competition. I mean, you've clearly all worked really, really, really hard, and the set of presentations were excellent. I'm going to announce the winner very, very shortly, so you've all been waiting very patiently. But look, I just want to say one quick thing in terms of tackling the global challenges as defined by the UN Sustainable Development Goals, upon which you've built your projects and submissions, has never really been more important. And last week, I spoke a little about the future of chemical engineering in my presidential address at the Royal Society of Chemistry, and how we have a vision for engineering a sustainable world. And chemical engineering really is at the heart of this transition, and our discipline works across all of the industries and products and things that we take for granted. Somewhere along the line, a chemical engineer has been involved designing it, operating it, developing it. And we've got a huge and unique opportunity to transform those systems, I think, for the future. So listen, I really hope you've enjoyed the process of the competition. You've beaten off many people to get here today. You know, I hope you've been inspired to think about choosing chemical engineering as a degree and a career going forward. As Gavin said earlier, it keeps lots and lots of doors open. So if you do chemical engineering, you can pretty much do anything. But now I think it probably is time to announce the winner. I'm looking at Cameron there. We took a bit of a while. We're a bit late coming back because we're really struggling to split the excellent presentations and the excellent projects that have made it through to today. But as we said, there can only be one winner, and I'm delighted to announce that the winner today is Breaking Bonds. Congratulations. Oh, you're on mute, Cameron. So I don't know if you.
Yeah. Oh, we can see some. Would you like to come online, Breaking Bonds?
You're on video.
Yeah, we are on video.
Oh, I think I could hear that. We do have a certificate, which is a bit strange to do virtually, but anyway, and it's probably going to get ruined by the background. But congratulations.
Well done, Breaking Bonds. Congratulations. So you will obviously get the prize from the Davidson family, as well as this. As part of the prize, you will also be arranging a visit for you to come up to Cambridge and have a look around. Well done, guys.
Thank you.
And as Mark said, you know, all the teams, well done. You all did a fantastic job. It was really difficult. It was really close between you all, and to be able to, you know, choose between you, we ended up having to scratch our heads for a long time. But well done, everybody.
And thank you for the response to all the questions.
Yes. So thank you, everybody, again for joining us today. Thank you for everybody for all your contributions and the questions. As Peter said, this has been a very successful competition, and I'm really pleased to see so much participation in this. So congratulations, everyone, again, and thank you so much for everybody's time today, especially Mark, Peter, Gavin. Thank you so much for your time today, and I hope everyone has a pleasant summer. Thank you very much, everyone. Bye.